Okay, so we're doing reactions of carboxylic acids, and we're actually we've looked at reactions of carboxylic acids as acids, and there's a whole bunch of those. Then we talk about conversions to the carboxylic acid derivatives. And we're now sort of picking up on, I guess it's another sort of preparation of the carboxylic acid. It's what's called a saponification reaction. And you guys may know from your basic biochemistry, or from just your general knowledge, that fats are really, well, many of them are long chain, are esters of long chain acids. And in fact, the carboxylic acids used to be called fatty acids because when the carbon chain was pretty long, they were found in many of the fats. The fats are glycerides, and the glycerides really are based on glycerol, which is a triol, and then what you simply do is you add carboxylic acids to each of these, or couple. So if I put 3 carboxylic acids, it's a triglyceride. And you know, for example, if you guys are probably too young for this, but you know, your doctor checks your triglyceride level. It's your fat level, and you can have diglycerides and so on. So they're all called acyl glycerides. But fats are really just, by and large, esters of long chain fatty acids. But I can convert the fat into what's called a soap, and a soap is nothing more than typically the sodium salt of a long chain fatty acid. And I can hydrolyze esters into carboxylic acids using H3O+, right? So if I use H3O+ and I heat, what I make is the carboxylic acid directly. But if I use the reaction under basic conditions, what I'll get would be the salt, the sodium salt of the carboxylic acid. Now, fundamentally, the reaction is a reaction between the ester and water to give the alcohol and the carboxylic acid. But under basic conditions, the carboxylic acid doesn't stick, and you make the soap. Just a quick note about the soap. You know, the way soap works is soaps don't really dissolve in water per se. What they do is they form what are called micelles, right? So they've got a polar head group, which basically then would be C double bond O, right, with a long, this is a minus charge, this is the resonance stabilized carboxylate, and then this is your C15, C20, whatever carbon chain. So I would consider this as having a polar head group and then a non-polar tail. So what we say then is that these molecules are amphipathic, right? In other words, they have 2 forms. One is polar, one which allows it to interact well with water, and the other one is non-polar. So I've got a hydrophilic side and a hydrophobic side. Or if you want, a lipophobic side, meaning fat-hating, and a lipophilic side, meaning fat-loving. Well, when I put soaps in water, what they do is they aggregate into what are called micelles. And micelles look like this. They would expose the polar head group to the aqueous film, right, and hide the non-polar hydrocarbon tail on the inside of the globule. This is called a micelle. Right, so I have the negative end of the soap particle interacting by hydrogen bonding with the water molecules, and the water molecule keeps the entire complex into what looks like a solution, but it really isn't. It really is more of a suspension of the micelles, because it's not a uniform dispersion. Well, you know, what happens then is when you put your dirty fabric into soapy water, you always agitate it. And most of the stuff that dirties the fabric is, you know, grease and muck. Grease and muck are hydrocarbons, right? Or certainly the non-polar. So what happens is when you agitate your soapy water, it impacts the fabric and the micelles scatter, right? The micelles break up, freeing the hydrocarbon tails temporarily. So those hydrocarbon tails interact with the greasy material by van der Waals interaction and pull it on the inside of the micelle. So they meet dirt, and then the dirt is a big particle, right? And that forms inside of the micelle, and the micelle gets heavy. So it sort of precipitates from the water as scum. and then you just rinse the scum off, and you eventually then just get the dirt off of your clothes. So really, it's a molecular interaction that's involved in cleansing. So that's one issue. But the other issue that we want to talk about is exactly how does the mechanism for saponification occur. I know I'm taking this species and in the presence of water, and I can either use H plus or OH minus as a catalyst. I'm going to make the corresponding carboxylic acid, we say, and the alcohol. Right, and I'm going to flag one of the R's. So I can, in theory, do this reaction one of two ways. Either the water molecule interacts this way. In other words, I have cleavage of the acyl carbon oxygen bond to give alcohol and carboxylic acid. There is an alternative, which is the reaction may go instead by cleavage of the alkyl O bond. So either I'm going to cleave the bond between the O and the acyl carbon, as above, the O and the acyl carbon, or I'm going to cleave the bond between the O and the alkyl carbon. And both of those would give rise to a carboxylic acid and an alcohol. Carboxylic acid and the alcohol. So the question is, which one do we get? And we should have a sense already which one should be right, because, we know if I were to get this reaction, fundamentally what would happen is I would have my water act as a nucleophile and attack this carbon, and I'd break this bond and carboxylate would come off. But that's an SN2 reaction. On the other hand, should water attack this carbonyl group, I'm attacking a carbon at the acid level. And if you remember one of the discussions we had earlier, as the oxidation level of the carbon rises, it becomes more reactive to nucleophiles, because as the oxygen number rises, the carbon gets more and more electron poor, more and more electrophilic, and therefore reaction with nucleophile gets faster. So I would have expected that the reaction should occur by cleavage of the O acyl carbon bond. Well, it turns out that actually is probably the way the reaction goes, because A, this carbon is more electrophilic, B, attack by water in that species results in the cleavage of a pi bond, at least initially. Whereas, and then C, this carbon is, as I said, well, A, it's more electrophilic. Here, the carbon is less electrophilic, and attack leads to cleavage of an alkyl oxygen bond, which is a sigma bond. But how can I test my hypothesis as to which mechanism the reaction follows? And the answer is, I do a nice simple study where I label the species. Let's say, for example, I label the oxygen with O18. If, in fact, the mechanism involves cleavage of the oxygen acyl carbon bond, then the O18 label appears in the alcohol. If, on the other hand, the mechanism involves cleavage of the bond between the oxygen and the alkyl carbon, then the O18 label is retained by the acid portion, and you end up with the O18 label in the acid, and your alcohol does not contain any O18 label. And it's very easy to look for oxygen 18 labels in your products. And in fact, when the experiment is done, it turns out that the label shows up in the alcohol. And therefore, we know that this mechanism is the one that is consistent with the data. And what we seem to get is cleavage of the bond between the acyl carbon and the oxygen. All right, so we've looked at reactions of carboxylic acids, and in particular their conversions to their derivatives. But there are a couple other reactions of carboxylic acids that we are particularly interested in. Oh, and by the way, carboxylic acids also can be reduced. Let me just take care of that immediately. Carboxylic acids can be reduced either to the aldehyde, right, with lithium, aluminum, tris-tibetoxyhydride, or all the way down to the alcohol if I were to use lithium aluminum hydride. In both cases, followed by water. Followed by water. There's an interesting reaction of carboxylic acids that is worth mentioning. So this is called halogenation, and the reaction is referred to as, interestingly enough, the Hell-Volhard-Zielinski reaction. And in the Hell-Volhard-Zielinski reaction, you take a carboxylic acid, you treat it with phosphorus, usually red phosphorus and iodine, and what you end up getting is alpha halogenation of your carboxylic acid. I can actually run this reaction with an excess of phosphorus and iodine and make a diiodo compound. And this, of course, is rather useful because it now means I could, for example, do SN2 chemistry on the iodide and put in a cyano group and then derivatize that, and all sorts, or put in a hydroxy group and derivatize that. So lots of things I can do with these reactions, right? Another interesting reaction is the reactions of keto acids, alpha keto acids. It turns out if I take a keto acid and I'm sorry, one second. Right, I'm sorry. Yes. So if we take not alpha but beta keto acids and we heat those, we get a rather interesting reaction. So, for example, if I take a beta keto acid, so carboxylic acid, this is the carbonyl carbon alpha carbon, beta carbon. If you heat beta keto acids, what they tend to do is they would spontaneously decarboxylate. And in fact, a better way of writing this would be, a better way of writing it would be to draw the beta keto acid in a form that looks like this. So I'm going to have my carbonyl, and then I'm going to have my carbon here. Let's say double bond O, OH. So what you see is that there's hydrogen bonding between the beta carbonyl and the OH of the carboxylic acid. And on heating, what happens is we do 1, 2, 3. So I'm going to have what looks like a 6-membered ring that has, in essence, 6 pi electrons in it. So it has some sort of aromatic stabilizing character. And in the end, what you get is the following. I'll have OH, double bond, and I would have lost CO2. I would have lost carbon dioxide. So what we get is a decarboxylation. Now this entity really is an enol. The enol will tautomerize. The enol will tautomerize into the corresponding carbonyl compound. So it means I can do what's called a decarboxylation of my beta keto acids and end up with the corresponding carbonyl compound, right? In other words, I can simply lop off that whole carboxyl group as a carbon dioxide unit. Now it turns out that reaction has potential value. And the value involves the following, and it involves a reaction of esters. So we're going to look at what's called Claisen, the Claisen reaction. So if I take a carboxylic acid ester, I should pick a specific molecule. If I pick a carboxylic acid ester, okay, let's pick, for example, OET. So look at ethyl, let's pick ethyl acetate. So let's take ethyl acetate as our example. If I treat ethyl acetate with base, an interesting reaction which very much resembles the aldol reaction occurs. So why is that? The proton here will be acidic, right? Because the conjugate base is resonance stabilized. So when I treat this species with, and I'm going to, rather than use hydroxide, I'm going to use ethoxide. And it's an important deal because whatever this group is here, I want to use as my base. And the reason is, in addition to doing chemistry here, OET, or whatever the species is, will do chemistry here. And what you get is a substitution reaction. So I want to make sure that this group is the same as that group, so I'll have no net reaction. Because if I put hydroxide in, then I'm going to end up with a carboxylic acid. And then there's a whole bunch of other things that's going to happen. Because I'll then deproton the carboxylic acid and make the carboxylate, and then chemistry stops. Anyway, so hydroxide reacts with the ester to give rise to the corresponding enolate, which is this species. Okay? Now, we've seen enolate before with aldehydes, right? Aldehydes and ketones can be deprotonated at the alpha H to make the corresponding enolate. And then what happens next is that the enolate is generated in a medium that contains its parent. The parent is electrophilic, so the enolate attacks the species. Now, we're all adults. What happens is the pi bond breaks first, and then comes back, and then eventually kicks out that species. So what you end up getting is this compound. Okay? So let's make sure we know our way around. So this carbon is here. Here's my carbonyl. This carbon is now here. Right? It's now bound to the carbonyl. And my other carbonyl group with the OAT is here. So what I have here now is a beta keto ester. Now that reaction is very much alike the aldol reaction, as we saw several weeks ago, almost a month ago. Right? In the aldol reaction, what we had was an aldehyde that we treated with hydroxide. And what happened? Right? The OH minus pulled off the proton, and we ended up with the resonance stabilized enolate. The enolate was born in a medium that contained its parent, so it scavenged the parent and generated this species. Right? What you got was a beta well, it made O minus first, which we then protonated. But what you got was a beta hydroxy aldehyde. Right? You got a beta hydroxy aldehyde. But in this reaction, what we get is a beta keto ester. And it makes perfect sense because at the aldehyde reaction, you're at the aldehyde level. Whereas in this scenario, you're at the acid level, so your product will be of higher oxidation. So this is at the aldehyde and acid level. And then this is at the alcohol aldehyde level. So because you're starting off one level lower, right, aldehyde versus acid, you're going to end up one level lower, right? So you're going to end up with, from the aldehyde, you get alcohol aldehyde. From the ester, you get aldehyde ester, right, or aldehyde acid level. So the Claisen reaction really is nothing more than a souped-up version of the aldol reaction. The aldol reaction is unique for reactions at the aldehyde level, but the Claisen reaction is unique for reactions at the acid level and really occurs specifically with esters. What is useful, though, is that having made the beta keto ester, I can do a couple of things with it. So I can take the beta keto ester, and then I could do interesting chemistry. For example, I could hydrolyze the ester using aqueous acid and make the beta keto acid. And why that is interesting is because I can take the beta keto acid, heat the daylights out of it, and decarboxylate it. And what you end up with is the corresponding carbonyl compound. Okay? So that gives you a rather interesting access to chemistry, because you can make the beta-keto ester and then eventually the beta-keto acid. It gets a little more interesting. If you look at the beta-keto ester, it has an advantage that the aldol did not have, and that is these H's are now very acidic. And so under the conditions of the reaction that generate the beta-keto ester, which is using ethoxide, that proton will not stick, right? With ethoxide present, that proton actually comes off, right? I deprotonate and I make the corresponding enolate. And that's wonderfully resonance stabilized by both adjacent carbonyls. Enolates are nucleophiles. We saw this with aldols. So this species can then be used to react with, say, Rx to do an SN2 reaction. R would have to be methyl primary. It works well with methyl and primary. You can do it with secondaries, but the reaction is a bit more lethargic because there's some steric bulk to the the starting material. And what that gives you is R. You could go back in, for example, and treat this with some more ethoxide, make more of the enolate, make more of the enolate, and then treat that with more of your Rx, and you would make this compound. So at will, you could make either this compound or that compound. And the beautiful thing is, both of these are beta-keto esters. So I heat this one with aqueous acid, and what do I get? The beta-keto acid, which is substituted. If I heat this one with acid, what do I get? The beta-keto acid, which is substituted. And you can well imagine that the next step would be heat them. And if I heat this one, what do I get? A substituted ketone. If I heat this one, what do I get? A substituted ketone. So it's a wonderful way of making substituted carbonyls using what essentially then would be a Claisen reaction and then substitution of the enolate with alkyl groups followed by hydrolysis to the ester and then decarboxylation of the corresponding beta-keto acid. Okay, so at this point we are done with organic reactions. All that's missing really is chemistry of amines, and the chemistry of amines really is fairly trivial. You see very few questions on amines. Most of that shows up in biochemistry. Plus, my feeling is once we've covered carboxylic acid derivatives and all the stuff before that, the chemistry of amines should be fairly trivial. So you have enough of an organic background, I think, to handle anything that comes your way. So I wish you guys really the very best of luck in your exams. I hope organic is good to you this semester. I hope you guys pass and do pretty well. And okie dokie. So, au revoir.